do I insist so much in the operator overloading? I insist so much because we will have fun with it. We will implement a machinery to automatically calculate the derivatives of a function just by writing the expression as it is. We will write a small matrix library that supports fixed size matrices and so on. For those that know eigenstyle, just like to become practical with it. And also we will have fun kind of profiling and figuring out what does it mean being fast. Okay? That's why I insist on this sort of thing. They comprise more or less modern C++. All right, so as I said, in C++ you can redefine operators, which means you can change the behavior of an operator when applied to objects or when applied to variables or expression of a certain type. In order to, what do you need to do to override something in general? You have to tell the rules, the system, when to apply that particular rule. When you override a function of a class or of something, you have to, you're going to the class and then you're selecting a method and rewriting the method in a derived class. The very same thing you have to do if you want to implement the override of operators in C++. Normally, like every operator, boils down to the evaluation of a assembly or whatever, a function. The plus can be seen as a function plus, which has two arguments, right? The minus can be seen as a function minus, which has two arguments, right? And therefore, by thinking about the overloading, which is different from overriding, overloading is the mechanism via which you can have multiple functions that have the same name, but they have a different list of arguments. And by looking at the list of arguments, you select the right one. You can implement the very same mechanism with operators in C++. There's a keyword operator. To redefine an operator, if you are in a class, you write return type, because it's a function as any other, operator keyword, operator type, plus equals, not equals, any of the operator lists that we have seen before, and then you put in the arguments. Which means that you might also, of course, an operator has a fixed size of arguments that has to be compliant with the rest of the syntax. Now, if you are overriding an operator, inside the class, clear, like we have done before with the equals, operator equals, right? We were inside a class scope, then the first argument of the operator is assumed to be the object of the class that you're writing where you're writing in. So the equals has two fields. If you override the operator inside the class operator equals, the first field of the equals, which is the left one, the one where you carry on the assignment, is self. This. Okay? And then it comes out that the other operand, the other argument will be the element which is on the right-hand side of it. But you can also do the overriding of an operator outside the class. And then in this case, you just write return type operator type, and you write the full argument list, which means that you could, if you would write the equals, I don't know if it is possible, but the plus for sure, you have to put two items there, the left and the right. Clear? Now, for instance, let's see the case of if we want to write an operator plus that calculates the sum, right, of two vectors. If we want to write this function inside the class, we would have to use this signature. First of all, plus. What plus should return? It should return a new vector, because the plus, if you do a plus b, you don't change a, nor you change b. So you have to return a new instance, right? You can't return a reference, because you have to create something different, something new. So, you return a vector. Operator plus, because a plus b, the first item is self, the second item is the other advent of the operator. Clear? Or if you do want to implement the operator plus outside the class, because you can also do it, no one prevents you from doing so, then you don't write the function inside, you write the function outside. But in this case, you have to put both arguments, left and right. You have vec f operator plus, vec f ampersand first, vec f ampersand second. How would they be implemented? Now, of course, I show you the stub as if it was outside in a CPP file. Otherwise, you just delete this and you copy it inside the class. What am I doing here is that I'm taking the result of the expression, which is other, the right-hand side. I need to create a new object, right? So in order to create a new object, the most intelligent thing that I could do is to invoke the copy constructor. Because the copy constructor will create an object exactly like a new instance of object, exactly as the one that I'm giving it, right? So I create a copy of myself. Vec f returned. Vec f, this should be capital. Returned this, no? And in return, I have a copy of myself. Then, if the size is different, in order to perform the vector addition, I have to ensure that the sizes are the same. Okay? Given that everything is at runtime in this case, I'd rather do the check. So if size is different from the other size, throw an error, right? And then you return. Or you could also just abort the system, burn the computer, do something. Okay? Otherwise, well, trivially, you loop through all elements of self and you do a plus equal of the corresponding value element of other, and then at the very end you return, which is the vector that you have created for addition. And in this way you could write v1 plus v2, and the system will digest it. Clear? Now, this is if you implement the overloading inside the class. If you implement the overloading outside the class, not much different, right? Like the only thing that you have to do is so I've been consistent with the errors. Now you make a copy of the first, then same check, and then the same for loop that sums the things into return. And then you return the new object that you have populated. Clear? This was one way of redefining operators. So we could have fun in writing expressions like that. Having the language still consistent and readable, because think about one aspect. When you program, when you work in C++, normally you work at library level. So you don't think about the application, you think about the user of your library. So it's very important for you to have a clean syntax for the person that will be using the system. Now there will be some Pythoner somewhere that will do some binding, assemble the thing and stuff. But you normally do the engine. Or you do everything in C++ as I do, but yeah. Okay. You can, with this mechanism, does it trigger to you, don't you have a tickling of implementing a funky matrix class with transpose, addition, inverse, and so on and so forth? I hope so, because this is what we're going to do. And then this basically concludes the thing. It's nearly 3. I bored you, I guess. Let me go gently through the exercises that I expect you to do the next time. The code, the stubs are not yet there. Wait until tomorrow morning, because now I have other stuff. But tomorrow morning you will have the stubs. The first is extended vec f class. We have encountered the vec f class, which is the one that we have seen. Now I will separate it into a CVP and into an H, so that it supports element access by reference. What does it mean? You have to write a function that returns the reference to an element at position I. Okay? It's very simple, very much closer to the act or get things that we have on there. Just to get the tickling of the references. Addition basically is done because I have pasted the code for addition. Then you have to do the subtraction. You can do it, eh? And then another thing that I'm asking is multiplication by a scalar. Like copy paste. Okay? So that you will have to implement an operator star that takes as input a scalar, a float. The other one is self. So if you do v times a float, then this will return a new vector where each element is multiplied by this. The final one is the dot product. Dot product means you have two vectors, v1, v2. You have to do v1, no, va and vb. You have to do va1 plus vb1. No, times vb1 plus va2 times vb2 plus. No, the dot product, right? Okay, and this is the first exercise. Then a second exercise, do you have it clear? Now I will write the stumps, but more or less the philosophy. Of course, there will be test things, it works, it doesn't work, all sorts of things, right? Second one that I want is that you write a binary tree that supports integers, that supports sorted insertions. It's quite simple. A tree is a data structure. Who of you doesn't know what is a tree? Has never seen a tree? You can raise your hand. Tree. Okay. A tree is a data structure where you have a node, and a left child and a right child. That's it. And then each child can have other childs or not. That's it. The childs are normally, everything is allocated on the heap. Maybe beside the first node, who knows. Yeah. Now, a tree that supported sorted insertions is quite trivial because I'm not asking you to implement a red-black tree, nothing like that. Do you know, for the computer scientist, do you know what a red-black tree is? Arbitrary, okay. It's a tree that stays balanced. That's a red-black tree. Now, yeah, I'd like to stand, but I can't because of the camera. That supports sorted, which means you have a tree and in the beginning you have one element in the tree, let's say 5. Then I insert 7. You enter the root and you see, is the node 5, is 5 equals to 7? No. Then you go right, assuming that right is it a leaf? Like, is there anything there? There's nothing. Create on the leaf a node which contains 7. And this way is done. Then I insert another node. Let's say I insert 6. 5. Do I have, is 5, is 5, 6 equal to 5? No. Then go to the right. Is 7 equals to 6? No. And then you go to the left of 7 because you want to have it ordered, and then you insert this node to the left of 7. Okay. If I tell you insert 5, you say no, 5 is already there. You don't do any insertion. So it's very linear as a thing. And you write a binary tree that supports sorted insertions and existence checks on the heap. Existence checks, basically I've told you the algorithm now. It's a recursion. If base step is I am in a leaf, or the value is me. If the value is me, I close the recursion. If I am in the leaf, I create a node. Otherwise, call the function on the left or on the right, depending on whether I'm larger or smaller than the value I'm comparing with. Okay? That's binary tree. But this has a little bit of a computer science touch, which I should not be expecting given the complete target, but you're invited to do so. But what I might expect is that you take the vectf class, you will take the implementation, the thing that I give you, the block that I give you, the header file, and then you will implement a C++ file that implements a matrix class, dynamic size, row major, supporting addition, subtraction, multiplication by a scalar, multiplication by a vector matrix, right? No, should be able to do the product to code the product vector matrix, and multiplication by another matrix of consistent sizes. I mean, given that you will have to digest platoons of linear algebra in your robotics course in particular, I mean, being able to implementing once a product matrix vector doesn't hurt, right? Okay, all matrix vectors. And these are the exercises, like, you know, to digest, have a look at. They are in increasing difficulty. They will not be checked. I mean, you know, one can also not do them, but I mean, I recommend you at least to try to do them, to try to understand the solution, in order not to lose the hook. Okay? And talking with you, you have told me that today is a heavy day, right? And I mean, well, now with Luca, we will try to move the exercise today, and to move to make on Thursday a massacre. Okay, or 2 hours of massacre today and 2 hours of massacre on Thursday. But not yet. First, I have to reorganize and redo the plan. So have fun while you're at home. Have fun, and yeah, cool down before the next hour starts.